Hi, folks. Today we're going to talk about chaos theory. This is one of my favorites. I always liked chaos theory. And so, what is chaos theory? Chaos theory is a branch of mathematics which gained popularity in the 1960s through the 1980s, primarily for these stunning visuals. You can see one of these on the right. That is a fractal. It is a branch of dynamics which was first meaningfully explored in the late 19th century, around the 1890s. But it wasn't fully explored until we had computers, because you really need computers to do some of this stuff. It gave us tools to explore fractal geometry, but more importantly, it helped us understand the complex nature of motion and develop new tools to explore these dynamic movements. It is the mathematics best described by the butterfly effect. And we're going to go and do a deep dive into it. And so let's see if we can understand what chaos is. Beginning with the three-body problem. This was one of the first big examples of where people were saying, there's this weird behavior that keeps coming up. How do we describe it? And so before we get to the three-body problem, let's talk about the two-body problem. And so the two-body problem refers to the motions of two objects in space, be they planets, stars, or whatnot. It is a problem from classical physics. If you have two objects of different mass that orbit one another, what is their orbiting path? How does the moon revolve around the Earth? How does the Earth revolve around the sun? If you have two things, how are they moving around one another? Newton developed calculus in part to solve this problem. And he did it. Newton solved it. Done. Two-body problem is solved. And so when two objects are orbiting in space, there is a point, which we call the barycenter, between the center of mass of the two objects, which both celestial bodies are orbiting in an elliptical orbit. The Earth and Moon orbit a barycenter, which is 2,900 miles from the Earth's center. The problem is solved regardless of the mass and beginning positions of the celestial bodies. Two bodies, no problem, it is done. The problem, of course, there are more than two celestial bodies in the universe. And so let's just bring it up one small step. Three bodies, three-body problem. And so how do three celestial bodies orbit one another? If you have the sun, the earth, and the moon, how do they orbit? If you have two stars of equal mass and a planet between them, what's going to happen? If the two-body problem has a simple solution, just ellipses, how hard could the three-body problem really be? It turns out it is extremely hard. And so in the 1890s, Henri Poincaré proved that there are an infinite number of orbits. While some can be simply described, most cannot. There isn't one solution. And so with the Newton stuff, yeah, two bodies, we've got a simple solution. Here, there is not a simple solution. It depends heavily on the initial conditions. And so what is the mass of these bodies? Where are they originally located? Is there any initial movement going on? Finding three-body orbits is an open problem in math, and every few years, mathematicians come up with new solutions to this problem. Over here to the right, you can see just a few examples, and hopefully you can tell they are all very, very different. That's the challenge with the three-body problem. Moreover, there are non-periodic orbits, which complicates things. And so Poincaré discovered that in addition to periodic orbits, there were orbits that just didn't reset. And so a periodic orbit is an orbit where all of the celestial bodies return to their starting locations and restart the orbiting pattern. Turns out you're far more likely to get a non-periodic orbit, where objects rotate around one another but never return to their starting locations. It's actually very rare that you're going to get it where they return to their starting locations. And these non-periodic orbits are much more common. That is definitely a problem. And so Poincaré and other 19th century physicists like Maxwell with electricity were realizing that this same behavior seemed to pop up a lot. Many occurrences depend heavily on initial conditions. Upon repeating an orbit or other process, the effect of those initial conditions can have greater effects, and you could end up almost anywhere. These conditions underlie what we now call chaos. And so let's see if we can come up with a working definition of chaos. The challenge, of course, is there really isn't a great definition of chaos. Well, actually, there's a few great definitions, which makes it even harder. How do you choose a correct definition when there are multiple good ones? Well, here's one that I like, and it's from Stephen Strogatz, who wrote the book on nonlinear dynamics and chaos. And so the way he defined chaos is chaotic behavior occurs when you have a deterministic system which exhibits aperiodic behavior that depends sensitively on the initial conditions, thereby rendering long-term prediction impossible. Those are a lot of big words. We're going to see if we can break down what this means. And so let's break this definition down. We have a deterministic system. What is a deterministic system? What is aperiodic behavior? What is sensitivity to initial conditions? And what does it mean to be unpredictable in the long term? Once we have a clear understanding of these characteristics, then we can explore some examples. And so let's begin with the idea of a dynamic system or a deterministic system. And so a deterministic system or dynamic system refers to some structure where actions have consequences. From a beginning state, things change in a way that we can determine or model how they are changing. This motion or change could be modeled one of two ways. It could be a continuous change, where we can model things using calculus and derivatives. Or it could be a discrete change, frequently involving recursion, iteration, or a difference equation. Discrete change, that would be like the Fibonacci sequence, where the next element is based on the two prior positions. Continuous, well, that would be something like this graph, where we can start to see all these little arrows showing the directionality of things. This graph comes from just a couple of little equations, but those equations describe this entire system. And this system is showing a lot of weird behavior. And so let's start with a continuous dynamic systems. A continuous dynamic system, we're often modeling things which are changing states without stopping. So it's continuously changing. Often we think of things like weather patterns, where things like temperature, pressure, and weather events are constantly changing. This also includes forces such as gravity, or the motions of a river, or something simple like mixing paint. These are things which, as you are doing them, or as they are happening, they are changing continuously. We typically model these things with differential equations and need to use a little bit of calculus. We'll avoid the calculus stuff for now. There's also discrete dynamic systems. These are a little bit easier for us to handle. And so in a discrete dynamic system, we are either one, dealing with changes which can be taken one step at a time, or dealing with snapshots of a system to simplify things. So for example, in population dynamics, the changing populations are typically discrete, but we often take annual snapshots to greatly simplify things. If we're modeling the population of bunny rabbits, we're not going to be looking every couple minutes at the population of bunny rabbits. We're probably going to take snapshots across years. Other systems, such as shuffling a deck of cards, can be taken one shuffle at a time and analyze the motions. And if you think shuffling a deck of cards, I mean, what is going to happen after 5 shuffles? It's difficult to determine. The next is sensitivity to initial conditions. What is meant by sensitivity to initial conditions? Well, it means that the long-term behavior will depend heavily on the initial states of things. A common example is placing a leaf on the surface of a stream. And so the leaf could quickly go under the water, or it could ride for a few meters, or it could go for 20 miles and out to sea. The difference of an inch or a second on your initial placing of the leaf could substantially impact the final position of the leaf. This is the sensitivity to initial conditions. Depending on the specifics of how you are placing it, you're going to have very different outcomes. The long-term behavior is generally unpredictable. And this is where the idea of the butterfly effect originated. And so in the 1960s and 1970s, mathematician Edward Norton Lorentz popularized the idea of chaos theory through the visual of a butterfly. His quintessential talk, Does the Flap of a Butterfly's Wings in Brazil Set Off a Tornado in Texas, gave chaos theory a visual which captivated the masses. The name the butterfly effect stuck and represents the chaos related to initial condition sensitivity. The idea being something as tiny as a butterfly flapping its wings could have monumental effects on the weather. How much of an effect? Well, it's hard to say. And that's where the long-term effects are often difficult to see. We then have the idea of periodic behavior. Now, that one's relatively okay to understand. We've seen periodic functions before in trigonometry, and so we know what it means to be periodic. Periodic behavior just means you're going to be returning to your original state eventually. And so periodic behavior occurs when a system returns to some earlier state and then begins repeating the same behavior. The phases of the moon are periodic, with a full moon occurring roughly every 29 and a half days. Celestial events, comet motions, solstices, etc., are typically periodic, as are things which vibrate or rotate in a fixed way. Periodic motions are highly predictable. Aperiodic behaviors are not. And so aperiodic behavior occurs when something is not behaving in a periodic way. If something is not returning to its prior position and repeating behavior, then it's aperiodic. This can take many, many forms. In chaos, we are mostly interested in aperiodic orbits, which cycle in a similar way to periodic behavior, but don't return to a prior state. And so imagine something which is repeating, but it's always a little bit off. That's what's happening with a chaotic behavior. The next idea is the idea of topological mixing. And so topological mixing is the idea that in a chaotic system, we will frequently see some repetitive action which will blur the starting states. Usually we think of it like mixing paint. If you start with red paint and blue paint, well, you can mix them together and you're going to get purple. But really, this purple is just a whole bunch of red and blue particles. But they are so mixed together that you can't really distinguish what's red and what's blue anymore. And that's where that purple color comes from. Our last big one is dense periodic orbits. And so often in a chaotic system, there are uncountably many aperiodic orbits. But near any aperiodic orbit, there's usually going to be a periodic orbit. In this case, we say that periodic orbits are dense. The idea that you are always really close to something periodic, but if you're on an aperiodic orbit, you're never going to hit that repeated behavior. Sometimes we're able to better understand the structures of the chaotic behavior by understanding the structures of the dense periodic orbit. And sometimes it'll look like we're following a periodic orbit, and then we'll bounce to something which is a different periodic orbit. So lots of weird things can happen. Now that we've gone over a whole bunch of different key terms, let's see if we can actually give an example of something which is chaos. Let's do some chaos. And the example we are going to go with is doubling angles. And so this is a classical example to demonstrate chaotic behavior, and it involves doubling angles on a circle. You can see all of our numbers, all of our different angles here. And so we have 10 degrees, 20 degrees, 30 degrees, all the way around. If we start at 20 degrees, we can double it to 40 degrees. At 40 degrees, we can double it to 80 degrees. At 80 degrees, we can double it to 160 degrees. And we can keep doubling. 160 would go to 320. When we double 320, well, that's going to give a much larger number. Oh my goodness, I'm going to need a calculator. I'd give 640 degrees. Well, 640 degrees isn't really on here, but also it is, because we could take that 640 and subtract 360, and we would end up somewhere down here, let's say. Yeah, that'd be around 280, I think. And so then we could say 280. What happens when we double 280? Well, we're going to get some other angle on here. And we can keep repeating this over and over and over again. And so recall the unit circle is a circle of radius 1 centered at the origin. An angle measured in degrees or radians begins at the x-axis and then measures in a counterclockwise direction. If you go 360 degrees or 2 pi radians, the angle measure starts over. What happens if we choose a starting angle and then repeatedly double it? Let's find out. And so let's start at 24 degrees. And we'll keep degrees for now because degrees end up being fairly nice. And so if we start at 24 degrees, which would be this red dot here, when we double it, we get 48 degrees. When we double it again, we get 96 degrees. That's going to be up here. When we double that, we're going to get 192 degrees, which is down here. When you double 192, you get 384, which when you subtract the 360 brings you back to 24 degrees. And so this is an example of a periodic orbit. 24 doubled goes to 48, doubled goes to 96, doubled goes to 192, doubled goes to 24. If we'd like, we can formalize this idea of doubling. And so this is a discrete dynamical system in that we get one point, then make a new point based on our previous point. We can even use a recursive formula. And so theta sub n is equal to 2 times theta sub n minus 1. And so theta naught, our starting theta, was 24 degrees. Iterating means that we are repeatedly applying this function. And so in doubling it, we got theta sub 1 is 48, theta 2 is 96, then 192, and then 24 again. We could say that beginning at 24 degrees, we see periodic behavior with a period of 4. What happens at 25? And so we did 24. How is it different if we start at 25? Well, here's the orbit for it. So if we start at 25, we go to 50, then 100, then 200. 200 leads to 40, which leads to 80, and 160, 320, 280. 280 goes to 200, which then goes to 40. Well, note, we've already had 240. We've repeated, or we've gone back to a previous angle. And so in this case, while we started with 25, we won't return to 25. Instead, once we get to 200, we enter a periodic orbit. 200 returns to 200 with a period of 6. Note that this was only 1 degree difference from the last example. 24 degrees, that had a period of 4. This ended up with a period of 6. And so our end behavior ended up being substantially different. What about 26? And so 26 isn't that different. But if we map it out, let's map out the path of 26, not 25. Clearly, I copy-pasted. And so if we are going with the path of 26, hide it by putting my mouse over it. 26 degrees goes to 52 degrees, goes to 104 degrees, goes to 208, 56, 112, 224, 88. And we can see it just keeps going and going until eventually we end up back at 104 degrees, which was the third one that we got. In this case, while we started with 26 degrees, we won't return to 26. Instead, we're returning to 104. And 104 returns to 104 with a period of 12. And then it'll just keep going in a circle. So 104 to 208 to 56 and so on until we hit 104 again. And then 208 and 56 and 112 and back to 104. And it'll just keep going. And so again, this was just a difference of 1 degree from the last case, and the end behavior is very different. What about 45 degrees? And so in 45 degrees, something even weirder happens. So 45 goes to 90, goes to 180, goes to 360, goes to 360, goes to 360. In this case, the function is no longer approaching an orbit, but instead it's approaching a single value, and it just stays at that single value. We consider such a point a fixed point. And so if you begin at 0 degrees, which is 360, you just stay there and you never leave that position. And so if we have any orbits which lead to 360, we just stay there. And so at this point, we're starting to see some elements of chaos. We don't really have chaos yet, but we're getting there. And so at this point, let's see. We have periodic orbits, sometimes called limit cycles. While some values start on a periodic orbit, others can enter into an orbit at later values. We also have fixed points, which are points which do not change once a value reaches them. We also see the start of the butterfly effect. And so if you look at the case of 24 degrees, 25 degrees, and 26 degrees, they all end up in very different orbits. This is demonstrating the sensitivity to initial conditions. What we don't have yet, though, is a periodic orbit. And so the question becomes, how can we get a periodic orbit out of this? Well, it turns out if we choose any integer degree value as our starting point, we will always enter into an orbit or approach a fixed point. And this is actually fairly painless to prove. This whole degree thing is really just a mod 360 system. And so if we apply the pigeonhole principle, eventually we're always either going to approach some value we've already hit, or we're going to end up with some fixed point. And so this will also be true of any rational degree. If we choose any fractional degree, we're still going to have that issue. The problem is degrees are just too nice. We set up degrees so that they would be nice. I mean, we wanted to make it so that we have a lot of nice angles that we can play with. In order to get an aperiodic orbit, we would need to start at an angle which isn't a rational divisor of the circumference. And the easiest example is a radian. What's presented here is the first 10 orbits starting with 1 radian. And so this one right here is the 1 radian mark. If we double it, we'll end up over here. If we double that, we'll probably end up down here. Double that, we'll just keep going around and around and around. Well, here is the first 100 iterations using 1 radian. And so the previous slide showed the first 10. This is showing the first 100 iterations. 1 radian is not a divisor of the circle since the circle has a circumference of 2 pi. This is an example of an aperiodic orbit. It'll cycle around infinitely and never reach an angle which it has previously attained. And it turns out there are more aperiodic orbits than there are periodic orbits. Remember when we said any rational choice you choose from the degrees is going to give you a periodic orbit? Well, any irrational version is going to give you an aperiodic orbit. And we know that there are more irrational numbers than there are rational numbers. And so this is going to be the case where we have far, far more aperiodic orbits than we have periodic orbits. And so what happens when we start looking at these aperiodic orbits? Well, here are 4 different colors that I've chosen as starting points. And so I've chosen 4 irrational starting points. Red is starting roughly at 13.59 degrees. Blue is roughly 35.34 degrees. Green is roughly 51.65 degrees. Orange is roughly 78.83 degrees. They're all irrational starting points, though. And I chose irrational starting points so that we can see what happens with the aperiodic behavior. The first 30 values of each orbit is shown. Now, all 4 of these, the red, the blue, the green, and the orange, all started in quadrant 1. It is hard to tell that we started in quadrant 1. When we look at all of this, it is hard to tell anything. It's hard to determine where things started. It's hard to figure out the orbits. There's not much that we can really determine. This is what topological mixing is all about. The idea is that after just doing a few orbits, we've seen that these four starting conditions, which were relatively close to one another, have now spread all over the place. And so this is chaos. While this doubling function is a simple example, it shows all of the characteristics of chaos. We have a deterministic system, and so from a starting point, we know where it's going to go. We have aperiodic behavior, and so when we choose an irrational starting point, we're going to get something which is never going to return to its starting location. We have sensitivity on initial conditions. If you're choosing a difference of 24, 25, 26, or any rational or irrational number between those, you are going to get substantially different outcomes. It is unpredictable in the long run. If you choose a random starting point, there is no determining where you're going to end up. We have dense periodic orbits. If we choose any of the degrees or any fractional degree, we know we're going to get a periodic orbit. And we have topological mixing. And so after going a few iterations, no matter where you start, you are going to have spanned the entire region. And it's going to be difficult to keep track of where things started. It also demonstrates some of the key features of general dynamic system, the idea of limit cycles, the idea of fixed points. And so this example really introduces all of the fundamentals of chaos theory. Let's talk about a lower level of chaos, the idea of bifurcations. And so that system that we just did, that exhibited everything that there is to know about chaos. Often when folks talk about chaos, instead they're just focusing on the butterfly effect, and they're focusing on how a small change in initial conditions can have drastic changes in the outcome. It's not necessarily chaos, but because of how popularized the idea of the butterfly effect is, sometimes it's treated as chaotic behavior. What the butterfly effect is really showing in this case is the idea of a bifurcation. And so we call an individual point where there is a divergence of outcomes based on slight change and in initial conditions, a bifurcation. If all of the points have bifurcations, then we have chaos. And so here's a simple example of where we can see bifurcations occurring. Consider the function x squared plus 2bx plus c equals 0. It is a quadratic equation, and we can solve it using the quadratic formula. We get x is equal to negative b plus or minus the square root of b squared minus c. What types of answers can you get out of this thing? Well, the types of answers you're going to get are going to depend heavily on the values of b and c. And if you remember from Algebra 1, we call it the discriminant. The discriminant in this case would be b squared minus c. Well, if b squared minus c is equal to 0, you get one solution. If b squared minus c is greater than 0, you get two real solutions. If it's less than 0, you get two complex conjugate solutions. If b squared minus c is a perfect square, you're going to get integer solutions. If b is equal to 0, you get a purely imaginary solution with no real parts. If c is equal to 0, then one of the solutions must be 0. And so just based on the characteristics of b and c, we can get a whole bunch of different things happening. And we can actually graph it. We can show where all of these different changes are going to be happening. When we think of all the different ways this solution to this equation can change, we find that it really depends on when c is equal to b squared, or when c is equal to 0, or when b is equal to 0. Well, here are all the different things that can happen. If we are in one of these regions, we are going to get some type of different behavior. If we are on one of these line segments, we are going to get some type of different behavior. And if you are crossing the line from one region to another region, that's where you're going to have the bifurcation occur. The idea is, as you're going from this region to this region, you're going to be crossing one of these lines. And so you might be going from the case of two real solutions to there being only one solution, and then, oh, now there's two complex conjugate solutions. Well, that's a bifurcation, where that small change in initial conditions can have substantial changes to the outcome. This particular example is very important in dynamics. And so when we start thinking about differential equations, Turns out there's only a handful of ways that we can describe motions, and they all boil down to this equation: x squared minus the trace times x plus the determinant equals 0. All of the different types of motion are based on this one simple equation, and the outcomes look like this. There are a lot of different outcomes based on what your initial values are for this delta and this tau. Yeah, note how different the motions look as you cross the curves. I mean, we have this one over here, which is a saddle point. We have a center over here. We have an inflected node. We have a node. We have a focus. Oh, there's so many different types. If you want to explore this, you'd probably need a biocalculus course or a differential equations course. We're not going to go in any depth into it. I just wanted to emphasize that there are some very big applications which come from simple equations. Let's talk about some more examples of chaos. Let's mix that paint. And so one example is fractal geometry. Fractal geometry is the study of geometric structures which have self-repeating elements. And so this example here is Sierpinski's triangle. It repeats the same triangular structure repeatedly. And so start with a triangle and remove the center, and then remove the center from all of the triangles that remain, and then remove the center from all the triangles that remain, and then repeat it over and over and over again. We get this type of geometry to better understand and measure a lot of different things. And for instance, how do you measure shorelines? Well, shorelines are infinitely complex. Where do you hold the ruler? What size ruler do you use when you're measuring a shoreline? It becomes very difficult. So understanding fractal geometry can give us an understanding of how to understand these infinitely complex structures. We also have weather systems. And so the Lorentz system is a tool in differential equations which is used to model atmospheric convection. It's how clouds are formed and how they can turn into rain, thunderstorms, tornadoes, etc. To demonstrate that there was chaotic behavior, he created a simplified example using his model called the Lorentz attractor, which is what this shape is. This is a shape which has an aperiodic orbit, and it's going to keep going back and forth between spiraling around this side and spiraling around this side. And we can start to see how it's going back and forth from one, and then it will bounce back to the other, and then it'll spiral before it'll come back to this first one. It'll just go back and forth forever. Another one is waves on a beach. Waves on a beach are highly chaotic systems. Every wave brings in grains of sand and takes away grains of sand. Which sand stays and which goes is highly dependent on your initial conditions. You can never walk on the same beach twice. And for that matter, life. Life is incredibly chaotic. And so the creation of the fundamental molecules of life are a natural consequence of chaos theory. The building blocks of life are just chemical combinations, and nucleotides such as RNA are able to self-replicate under the right circumstances. And so when we start thinking about fluid dynamics, which has substantial chaotic behavior, we can start to see the mixing of chemicals, which are the building blocks for life. We don't know the exact mechanism used billions of years ago, but what we do know is we do know that chaotic systems like this can lead to life. And we've even created it in a lab. And so folks back in the 1950s, I think, I could be wrong there, were actually able to generate the building blocks of life just from simple mixtures. And so having chaotic systems, we're able to create life from nothingness. And here's where a lot of scientists think that the origins of life come. So the earliest known life forms are putative fossilized microorganisms found in white smoker hydrothermal vent precipitates. Yeah, and so we can model all of this stuff, and we know exactly how this stuff happens, and it's all just chaos theory. Final thoughts. Chaotic systems are all around us. From the air we breathe, to the mixing of paint, to the motions of the stars, to the formation of life itself. While great emphasis was placed on studying it in the 1960s through the 1980s, this was largely because it was uncharted math. and computational technology was finally advanced enough to do a deep dive into the structures. These days, while chaos theory is still a field, it's not typically studied in as direct a way. Instead of being independently studied, it is more viewed as a feature of other fields. Dynamics, in particular, views chaos as a natural consequence of many continuous differential systems. And so when we are thinking about chaos theory pops up in all the fields. But usually we are focused on other things. The idea of aperiodic orbits, it's fun. It's something which is always going to be present. But once we understand that it's always going to be present, it becomes a question of what tools can we use to understand these chaotic behaviors? How can we model them? And beyond that, there's not much more we can do. We can't find a general solution for a chaotic system. And so the best we can do is create strategies to try to understand them. With that, I'll let you get to work exploring where you find chaos in the real world. Good luck, folks.